Hello, everyone. Good afternoon. Can you guys hear me?
Yes, sir.
All right, great. So we are going to cover a new topic today, which is RNNs. Should be a pretty interesting topic. You will have a homework assignment on this that I think you're really going to like. Let me just get to it. Okay, here we go. So here we are. Or next page. All right, so recurrent neural networks. This will be our topic for today. So remember, I'm recording this video. I'll post it on Blackboard, or sorry, on YouTube later today, hopefully. So, you know, been pretty busy with everything, but once I'm done with this lecture and my next class, I should finally, things are starting to die down. So I promise I'll have your exams and I think one homework graded by this Friday. Okay, so if you definitely want to have that done for you guys. So before I continue, before I start, I guess, with, because remember we basically wrapped up convolutional neural networks last week, right? So you guys have an exam similar to that, and then we went over the solution. Okay, so now, you know, we've wrapped up convolutional neural networks, and today we're going to start the topic of recurrent neural networks. So before I get started with this topic, are there any questions about anything? Maybe questions about your project or questions in general? Are there any questions? Okay, so no questions, it seems. So Mendra, can you hear me? I saw you come in. Mendra?
Yes, Professor.
Can you hear me? All right, yeah, so, and I see Drew just came in. So guys, before I get started, are there any questions? No questions? All right, so I think there's no questions, so therefore we're just gonna get started with the topic, okay? So recurrent neural networks are pretty good. Pretty interesting topics. This would be the one topic that I haven't done that much research in, recurrent neural networks, even though they're a tool in natural language processing. So I'm going to talk, before I get into like the code or anything like that, I'm really just going to talk about the motivation as to why, right? So recurrent neural networks are the deep learning version of sequential machine learning. So sequential machine learning, it used to be for many years before, you know, 2010, that for decades basically, that we had these methods called hidden Markov models. So obviously that started with Markov models, and then from there, hidden Markov models. So that's more of a course, you know, I would cover in the machine learning class, not a deep learning. So hidden Markov models were the technique for dealing with sequential processing. And what I mean by sequential processing is basically whenever you have a situation where your data, so I want to kind of illustrate this. All right, so let's imagine, so usually what we do is, we look at let's say an instance, right? A sample, an image. And then we just say, you know, if there's a cat, right? We say, you know, cat or dog, right? That's usually what we do when we're doing, you know, machine learning, or at least that's what you've looked at. However, there's a different class of problems which can't just look at now. All right. So basically, what sequential models do is they look at a sequence of events. Now that sequence of events could be, you know, a sequence of events over time, or a sequence of events, you know, I guess everything technically is over time, right? Because if you have a sequence of events, one has to happen, you know, before the other one, right? So you can't really have, you know, I'm sure there might be a situation where sequential models could be used and time is somehow the same, but let's just imagine that here, whenever we do this analysis, you know, we just look at time one, right? Time one. All right, and then, but we don't really look at the information at time, let's say time I, and then we don't look at time I minus one. So we don't really look at that, right? You know, it's not like, well, this is a cat, but if I look at the previous image, you know, it actually turns out that this cat, you know, was something like this. And now, oh, wait a minute. If I look at it from the side, guess what? That's not a cat, that's a dog. You know what I mean, guys? Does that make sense?
Yeah, Professor.
Yeah, so that's basically the, you know, the idea with recurrent neural networks. So with this example that I just gave you, what comes to mind to you if you're dealing with images? What would come to mind? What type of information could this be? So if we looked at images, right, you know, it might make sense that these could be videos, for instance, right? So if you know a video is really just frames of images over time. You see that? So that's one way of thinking about it. Another way of thinking about it is, you know, I want to predict the following. I want to predict, you know, the sequence of consumption of ice cream, right? So here's ice cream, right? And here is the weather. So this one's the weather, right? So if I see that today is rainy, sunny, what would you guys say about ice cream over here? What would you say on this day? Ice cream or no ice cream?
Sunny or rainy day?
This is rainy,
No,
sunny.
No ice
no
cream.
ice cream, no ice cream, ice cream.
Exactly, right? So you would see something like that. No ice cream, ice cream. You see that? And in between, guess what we have if these are neural networks? Come on. What do you think we have here? Hidden layers. We have
Yeah.
to learn. And what's going to happen is, because they're sequenced now, you also predict in that direction. Do you see this, guys? So the information from the previous state becomes an input, just like the current observation for this layer. And then this layer can predict what the current state would be there, but it can also continue to predict, given the output here, what the value is. If you just want to know, let's say this is Monday, Tuesday, Wednesday. If I just want to know the ice cream consumption of Wednesday, all I have to do is grab this node. So it's actually, I don't necessarily have to always look at the sequences. I can always pick the day that I want, because this would be, you know, ti, ti minus 1, ti minus 2. Does this make sense? Okay.
Yeah, Professor.
All right. All right. So that's basically the premise of, you know, recurrent neural networks. That's really it. I mean, that's, you know, it's a simple concept. Okay. So let's think now. I want to give you a few more intuitions of this, right? So, and like I said, you can apply this to a lot of problems. So I know, for instance, Joe is working on financial information. So he might tell us, you know, I might, so what I might do is I'll try to remind me to try to apply this to your problem some way, and then you correct me, because I'm sure I'm going to, you know, not really capture your problem at all, but, you know, you know, so just so that we have a point of discussion. Okay, so another example you know, I want to give is, you know, before we get into the code and everything, I'm actually going to use all this white space I have. So another way of doing it is, let's say that I, you know, for whatever reason, I want to infer, so there's shadow, right? So there's shadow or something. There's some kind of you know, I don't know. Let's imagine there's a car over here. It's going, actually, looks like it's going in that direction, right? And so, you know, and then over here is like, you know, in cartoons, right? So something like that. It looks, you know, like it's going like that, you know, going, you know, the idea is going really fast. Okay. And so another way of doing it is, you want to know, is this going fast or slow, right? So in this example, since you guys are experts in image processing now, you could just say, well, I'm just going to apply a CNN, you know, and you know, convolutional neural network, and I'm going to build a classifier, and that's going to give me my result. Now remember, RNNs, just like CNNs, are supervised. Okay, they're supervised. So you have the data. Okay, you have the data, you have the labels. Only the labels are now sequential. So one way of processing all of this, if this is an image that is 28 by 28, is doing what? We take a snapshot in time. This is going to be TI, right? And then we're going to stretch this vector to 784, right? And then we process it through some machine learning, right? That's usually what we do. However, in this example, it might make more sense to look at the sequence of events. I want to know, for instance, that in this slide here, there's nothing. Then I want to know that in this slide here, oh, look, there's like a little dust, you know, picking up speed, right? Then you have over here, you know, you start to see the car. You see that the car angle is kind of like, because of, you know, the wind, like in cartoons maybe. And then you continue like that and that. And so you're really analyzing the image, you know, in a sequence, right? So now you're saying, well, I looked at it, you know, let's say this is time I, so then I looked at it at 10 I minus 1, then 10 I minus 2, then, you know, and dot, 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 10 I minus n, right? So I looked at it over time. And so now what you could do is, well, I'm going to train my recurrent neural network, and, you know, there's information here, right? There's information here that's associated with that, or there's no information there, but there's information here. So you can say that the label is at the very end, right? So that, you know, that, so only this vector has a label, for instance. You can think of it that way. But there, in theory, though, the recurrent neural network will also figure out what this information is, because it gives you sequences. So the output of it is a sequence of labels given a sequence of inputs over time. Okay, so then now I'm going to, when I build my recurrent neural network, this vector becomes the first input. So now this is a vector of 1 to 28. Then this vector becomes the next input of 1 to 28. Then this vector, 1 to 28, and so on. So you keep doing that over time. And then at the end, so then you have these inputs. Okay, once you have those inputs, you're going to define hidden layers. Just standard hidden layers, or actually, we're going to use something called the LSTM RNN cell. Okay, but it's basically this. Okay, and then this will have a sequence of outputs. Right? And so the only thing is the RNNs are also connected like this. Okay, so that connection through this idea, you get to do it. And then there's an activation function here, like always. We're going to have an activation function. Oops. Okay, and so these become the labels. These are one-hot encoded, just like you would expect. Okay, one-hot encoded. All right, and that's it. Now you want to know, is this going fast or slow? Well, this one could capture that fast. So basically, it's like you're saying, well, here I think it's going slow. Here it's going fast. So it's going fast, right? And so you can infer really over time, you would infer the speed of it. So slow, it started slow, but then fast. And so it kind of, ends up being fast. And then at the end of the day, we can just pick this label whenever we want to label the entire image, or we might pick individual levels if we want to know a sequence. So like the example I gave you of the sunny versus ice cream. Are there any questions about this? This is all clear? Okay. So anyway, so let's do
Professor,
another.
I have one question.
Yeah, go ahead, please.
Is there anything to do with the
Can you
rotation
speak
of
up a
the
little
angle?
louder, please?
Is there anything related with the angle of the image? Like if it is like all the way like 180-degree downward, and if the image is reversed, does it's gonna affect anything with the learning process?
I didn't understand what you said, Sumendra. What do you mean? Can you explain?
So right now, let's imagine when we feed an image, right?
Yes.
And the cat is facing vertically upward,
Like that?
90-degree. And if we rotate the cat, if we feed the image with rotating the cat now facing the head downward, does it's gonna affect anything?
Do you mean going like that? If we fed this one, is that what you mean?
Yeah.
Well, it depends on what this label is, right? That's what it's learning. Remember, it's learning to it. So remember, machine learning is about always correlating the inputs to the outputs, right? Do you see that? Sumendra?
Yes, processor.
So what are the inputs here? The inputs are the slices. So this slice of image is the input, right? It's a vector of just 28 features, 28 pixels, right? That's what I give the model right here. So I give it this, and then I associate with it the output that I gave it. So I train, you give it some training data here as well. You see that?
Yeah.
Okay. At the end of the day, if you're just looking for this one and you don't care really about these, okay, that may work fine, right? Because at the end of the day, it's going to associate this one to this one, just taking into consideration that it starts here, then it goes there, then it goes there, then it goes there, go there, there. So it does take into consideration the previous data. What I did here is I artificially break this, I split this, right?
Yeah.
Into the slices. So that I end up with 1 to 28 of these, and these are of size 1 to 28. And then I feed them like that, you know, for this example that I gave you of doing this like that. Obviously, a video is a cube, right? It's a very, very, very long cube. Let's say your image, I don't know what high definition is, but let's say you compress that to 250 by 250, and then you know you have what in I know in like movies it's like 24 frames per second or 30. Okay, that should give you enough for you to get the feel of a video. So then imagine that's 30, and that's just 1 second, and you know then we take a clip of, you know, I guess just a minute. That's 60 times 30, right? And so that's your cube. Do you see that, Sumendra? Make sense?
Yes, Professor.
Yeah, so that's the idea. So I'm only applying, you know, I'm trying to apply this to a video processing, which you certainly can try to do. I'm sure you could connect RNNs with CNN techniques, right? Convolutions in there. I gave the example of, you know, ice cream and Sunny. Let's look at another example. So let's look at the migration of birds, right? So let's look at the migration of birds, and let's think about this problem. So stop me at any time if something doesn't make sense, okay? So stop me at any time. So here's another example. So let's imagine we have the migration of birds. So we have birds, and then this is Spain, France, Italy, right? And then England over here, and then this is Africa, right? So, so let's say you have the birds live over here, right? So birds. And then the birds start migrating, right? And they move, and then they move into Africa like that, right? So that's the basic scenario there. So the question is, you know, you have sensors, and this is because some students are doing this project, right? So let's imagine now, let's simplify it, and let's just say you have this, right? So you have north, south, east, west, right? You have that. And then so you have a map, and the birds are there, birds are there, birds are there. You want to see how they migrate. So they go, you know, you put sensors on the birds, they stop there, they do this, I don't know, they move that way, move that way, that way. For some reason they go back at some point because there's a lake maybe. Do you see that, guys? And then eventually over here, this is Africa somewhere, and this would be Europe over here, and they have to cross the Mediterranean, right? So let's say that I gave you on the exam this problem, and I asked you to model this as a recurrent neural network. What would you do? What do you guys think? You need, so think about it, right? This has to be a recurrent neural network. So you have to model it as an RNN, which means what? You have to have some inputs. And then hidden layers. Right, so these are the hidden layers. These are the inputs, and then these are the outputs, right? So what do you think? How would you define an input vector? How would you define an output vector? Remember, what you're trying to do is you're trying to figure out the sequence, right? The sequence of this.
It will be the direction, professor, like from which the direction from on a globe, like north.
Yeah, let's say that you have here the latitude and longitude. You have latitude, like on the GPS data, right? You have GPS. Oops. GPS data, and that gives you the latitude and longitude for the birds here. And then you take it again here and so on. So you have that information. And given that you want to predict their migration, right? Their migration. So this is migration. And then this is position based on GPS. And, you know, keep in mind, you know, many of you might have different approaches to this. So I just want to, you know, I missed this in the classroom, right? So having this, you guys solve a problem. So what do you guys think?
We can check the wind direction.
Sure, the wind direction could be a feature. So one of the features, so, you know, wind direction, why not? You know, if a bird is flying, right? You know, a bird is flying and, you know, they're like, they don't want to exert themselves. If the wind is blowing from that, even though their trajectory was like that, they're going to really end up kind of like that. And they have to correct. So sure, it makes sense that wind direction could be a feature. What else? So you guys, latitude,
temperature,
wind direction, what else? What do you guys think? What about where they, let's say that you're here in this position. Well, what about knowing this from the previous position? You see that? Does that make sense? If you know, look at this, they're going straight, right? So if they were going in this direction here, there's a possibility, probability is a little slightly higher that the next one will be in that direction versus going in that direction. You see that? You see what I'm saying, guys? Now that feature, it doesn't necessarily have to be here, right? Because that is captured by the recurrent neural network, right? The fact that, you know, you have this, you ended up going in a, you know, here, given that here, this led to that, right? You guys see that? So do you think there's a need for additional features? Anyone?
Yeah, the months.
The what?
Months. The season or the months.
Mm-hmm. Right. You want to know if it's winter, summer. Okay, so that's another one. Season. Makes sense. And so on, right? So let's just say, let's leave it there. I'm sure there can be a lot of data there. All right. Now, so these are the features. So how many, let's say we pick only these 4, then how would you define the dimensions of these vectors? What is the size of this one? 1 to what?
4.
4, exactly, 4. Very good. Right, that's what I'm trying to show you is that these are the features, right? Just like with the image, 1 to 4, 1 to 4, 1 to 4, 1 to 4. That's your observation at each point, correct? Because maybe you're just tracking like 1 bird or you're tracking like 5 birds, but you're averaging them out, correct? Now the hidden layer is just like any other hidden layer. You specify the size of it. So let's just say, you know, well, this is 1 to 4. I'm going to give it size 10. Okay, so each one of these is going to be, you know, from 1 to 10. 1 to 10. 1 to 10. 1 to 10. Is that clear, guys?
Yeah, Professor.
All right, great. Now, what about the output? What's the output going to be? Obviously, you need the data, right? You need the label data there. So what do you guys think? What is so the output vector has to be one hot encoded, right? It has to be one hot encoded. So please tell me the dimension of this. What are you predicting? What do you want to know? Right? So if you want migration of the birds, what would that be?
Migrating and not migrating.
They are migrating. So what you want to know is how are they migrating, right? So you want to predict. Remember, this is a sequential thing. So what you want to predict is, you know, this, the overall direction that they're going to take. You see that? Considering that they'll do strange things like go around something because maybe they found food here. And I don't know anything about birds, but just saying. So what makes sense to you as outputs? Come on. The simplest thing.
1 by 4
Right.
against 4.
1 by
Like
4. What are the values? Sumendra, you said something. You had a thought there.
Yeah, Professor.
What?
It could be any one of those features. So
Okay.
we're trying to detect the direction, right, Professor?
Yes. You want to detect, you know, that it goes like that, right? You know.
That will be the sequence of image. That's what we are trying to trace.
It's not images. It's just a sensor that, you know, the bird has on its leg. Got a little. It's been tagged with a little sensor.
so, Professor, there should be 4 outputs: north, south, east, west.
Okay,
Right?
that's a good one. You know, or it could be north, east.
Uh,
What is it? Southeast, south, southwest, west, northwest, north. Perfect. Do you guys agree?
Yep.
Everyone? And if you have other ideas, that's fine too, but that's a good one, I think. How many is that? It's like
6.
it's 6, really? North,
1, 2, 3, 4, 5,
east,
6, 7, 8.
east.
8.
This
It will
one,
be
that one.
yeah, 8.
So there's 3, 6, yeah, there's 8. 8 of those, right? So it's size 1 of 8. So basically, you're producing a one hot encoded vector on each one of these situations, where because you're going to use a softmax, right? So you guys should know by now. You use softmax or something similar. It's going to basically select the index of the highest probability, right? And so what does that mean? It means that it selected that one, here it selected this one, here it selected that one. So basically it means for this observation, they went what? It went, let's call this one west, right? West. This one is more of a southwest. What is this one? Guys, what is this one? South, right?
Yep.
This one, let's say west, south, definitely southwest. But here they went northwest. Then they went southeast. Then they went south, basically. Then they went southwest again. Then they went south. Make sense?
Yep.
And that's it. This is you just built a recurrent neural network. Exactly like that. You want to know, for instance, trajectory, you take the entire output, because the RNN will give you as an output that sequence of vectors. So it'll give you a tensor that will have, let's say that there's, I don't know, 20 observations and 8. So it's going to give you a 8 by 20, right? 20, 1 to 20, and then 1 to 8. Tensor in this case, right? If you had images or something, it would give you cubes, and, you know, so it's a tensor at the end of the day, but that's all you're doing, right? So here we modeled the entire model. Now let's say that I want to know where they're going to be at time, because they start here, right? So they start at, you know, this is T, you know, Tn, and then Tn minus 1, and so on. Tn minus 3, and so on. So you can tell where they're going to be, right? So I give it the model, but I want to know where they're going to be at the end. So they're going to be going south, right? So they're going to be going south. Or I want to know where they're going. And if I want to know their entire trajectory, I just look at the entire sequence and I can basically go. Obviously, you need to know how fast, but you know how fast birds fly, right? So you know how over time. So, you know, so things like that. So this is the basic idea. Obviously, you're going to be modeling this for a specific type of birds in Europe, in migration, you know, and it gives you some idea of where they're going to end up versus them ending up, if they had more of a southwestern, so if they just flew southwesterly, they would end up like that, correct?
Yeah, Professor, I have one question.
Yeah, please go ahead.
So the learning process, the data that we feed, is it all based on image, or you just
No,
talk
this
about?
is, well, this example is not image, Sumendra.
Yeah, because I just got confused. Like you just gave an example of an image earlier, and then you told me like you just told like there is a sensor that is attached to a bird feet.
Yes.
So it could be any data, right, Professor?
It could be any data, Sumendra. That's exactly why I gave you an example of an image, to show you that it could be image data. And then now I'm saying, you know, this is a bird, right? And the bird has a little sensor there that just sends radio information to the GPS, or, you know, satellites or whatever. And then it only records, look, your latitude, your longitude, your wind direction, season. Those are the 4 features that you guys define. But we also know, because of this, that it was going west, because we know, well, at time T, they were, you know, west, and then they were at T plus I, TI, I plus 1, they were at 20 kilometers you know, southwest of their original position.
Okay, Professor, I have one more question. So
Yeah, go
can
ahead.
we use RNN to feed data that's learn like the basic migration process of a bird? Let's say if there is something which is like moving, let's say there is a satellite which is moving over the sky, and then we are feeding the positioning when they are just revolving around. And if they change the course of their direction, can we use the same method to put them back onto the same course, something like that, the alignment?
Okay. I forgot I had this whiteboard. So first, all right, let's go to the whiteboard here. I'm sorry, Sumendra, can you, so you have a satellite, you said, right?
Yeah.
Okay, so this is planet Earth, and then you have a satellite over here. Okay, and what's going on with the satellite?
And then like in case of our bird, we are using satellite as an our feed, right? Because that's how we are collecting the GPS position.
Okay, so you're still worried about the birds over here. Okay.
No, Professor. Now, in case of satellite, we have to use ground as an our reference, right? There will be multiple
Multiple satellites?
No, there will be multiple like the places, like the site where they can locate the movement of a satellite in Earth, around the Earth, because it's basically satellite is revolving around the Earth, right?
It's in an orbit, right? It's in orbit. So the satellite is in orbit. I mean, satellites don't have like a rocket or anything, right? They're just in orbit.
Yeah, so it's basically revolving around the Earth.
Yes,
So
they are.
now,
Yes, yes.
to know the course of the satellite, we have to have a base station in each and every place in the Earth so that they can collect the positioning when they are moving.
Okay. Triangulation, right?
Yeah.
Mhm.
So
Okay.
now let's say if like these different position in the Earth, now they are feeding data based on the course of the satellite when they are revolving around. And then we feed that data to our RNN to learn like how they are revolving.
Okay. And
And now, can we use those data to change the course of the satellite or the speed, like, like, because now we are detecting. So can we use our machine learning RNN like method? Like, let's say if
so
such
you
satellite,
basically you want to know by their, let's say this is the orbit and you know what the orbit should be. You just want to know if the satellite is like in orbit, and if not, it should like fire its rockets and get back into the.
yeah, when they change, like when they just change the course, like because there is when they are keep on revolving around, they might have like change the course because now we have base station which can keep on learning their data, like the positioning when the satellite
Okay.
is orbiting. So if we want to put them back in a course, if they are moving away
Yeah,
from the
so
course,
you basically want to use an RNN to put them back on course.
yeah,
That's.
because we are learning, right? Because from RNN we are keep on learning. So
Yeah, I think, this is governed. Well, first of all, I would say, physics is pretty, like, there's no resistance in space, right? Unless they crash into something, they have an orbit, and I think like Newton's equations or something, Einstein, whatever, will keep that thing on where it's supposed to be. First of all, that would be my understanding of it. But that being said, can you use an RNN to learn? Sure, I think so. I mean, now how would you do it? I think it's the exact same thing. That you measure, you send a signal, right, and then you get it back, and that measures the time, and so that gives you distance because we know the speed of light or radio frequencies. And then we check in their position. That's how triangulation occurs, right? I think, and then they figure out the coordinates based on that. So if the satellite was slightly closer, I think, yeah, you could, move it, and then so the features would be, um, something like, I think the output probably is like altitude and position. I don't know in space how they do it. There's no latitude and longitude in space, right? that I know of. So I don't know what the output features would be for a satellite. And the inputs over here would have to be based on like speed of the signal getting there and some kind of triangulation. I mean, I'd have to know more about, the physics of a satellite, but is that what you mean, Sumendra?
yeah, something like that. Just because I just want to see like, can we use RNN to train the
Well, you would certainly, so without knowing things, let's say you would certainly know the altitude and the position, right? Because it's checking in. I think, I'm sure they have the
because
science that does that, right?
yeah, professor, because what I'm thinking is like the
Yeah.
application, like it's not only about like once we have an output, we have to apply it to something, right? It's just not we are trying to view the output. I'm just trying to think about the
Let me put it this way.
like after we learn what's the application, that's what like the bird migration, we're going to use it for some kind of like the migration process of the bird.
Yes.
Like if there is something like which is in real world scenario, and then if we use RNN to train our
But you
model.
can't, I mean, the migration of the birds is actually a thing. I mean, people might, So because the birds might be going on a more westerly direction or a less westerly direction. So they want to know where they're going to be. Actually, it's interesting.
Even like, let's say, Professor,
For pandemics, huh?
let's say the aerospace, like let's say the flight navigation or something like that. There is
Are
a
you talking
routine-
about airplanes or satellites?
Yeah, aeroplane now. Let's say like now bird will be an aeroplane for us.
You want an airplane, okay?
Yeah. Now they have a fixed path, right? That, Professor, they always use for different countries.
Okay. So you're going from point A to point B.
Yeah.
And you have a little airplane, right? Okay.
And they are using a specific direction for each
Sure.
country. Like from one country to the other country, they will have a specific path, which might be just changed on the base of altitude, but they will basically follow the same route. Or there might be an other alternative route, but it's still in the space, like from one direction to the other.
Mm-hmm.
Now we can feed those traffic as in bird too, right, Professor? And
Sure.
we try to, and we try to.
You want to predict. So think about. So this is
some planes get missed. They didn't contact to the radios. So at that point, can we
Right.
use this thing as an application measure to analyze, like we are collecting the traffic, and from at what point we just lost it?
Let me put it this way. I have a good example of this, I think. I'm making this up as I go, so help me out. But do you remember an airplane that went down over like
The Malaysian flight?
Malaysia? Yes, Malaysia, right? So they knew the planes check in. They checks in here, checks in here, checks in here, right?
Yeah.
But after that, they lost radio contact, but the plane continued to fly. Now, depending on how it went down, it could have gone straight, could have gone in that direction. If the pilot intentionally did something, he could have just done that. You know what I mean? So if you're a Navy, right? The Malaysian Navy, and they want to find, they got ships, right? And the ocean is pretty big, so they can't cover this entire area. You know what I mean?
Mm-hmm.
And so in that case, they probably want to figure out. So the problem, I don't know the solution, let's say, but the problem I can certainly think that it would be, they want to say, well, they're flying in this direction. So if you guys are smart. If you see the plane flying in this direction and you know it crashed within an hour, so it never went past that, where would you look? Probably look like that, right? Something like that. That kind of makes sense, right? You look at the limits of where it went down. Other people might just look at a radius like that because the pilot could have turned the plane and crashed it intentionally. So it's really, not clear. So then in that case, you could say, well, I want to model an RNN, right? So one thing that's important in flight is wind. Airplanes live by wind, right?
Yeah.
They also live by weather. Winds push it. So if the wind is blowing in this direction, well, the plane actually had a tendency that, right? So it's, also if the wind is blowing from the back, the plane was going really fast because it's pushing it, those things. So that already tells you some of the features that you want to probably look at. You know what I mean?
That's how we're going to train our RNN from earlier, right?
Let's say it again, sorry?
We're tracking the same plane over year, let's say. That's how we are feeding our RNN. And then we have enough data.
Yeah, you have to have these positions. I mean, you're not going to not use that if you have it, right?
Yeah.
Because you know the time when this occurred, you're going to say, well, you know what, the features are these, and it's going to be like wind and weather, because you can get that at 3 p.m. on a Saturday, March 2020, this weather and the wind. You can get that. Okay, so that's recorded. And then you knew that the plane checked in and it gave you an altitude, speed, and so given those would be some of the features, I think. You want to look at the weight of the plane, if it was full or not, and so on. So I would think those are your features right there at each position. And at each position, you also knew, well, it was flying south, 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 south. Do you see that?
Mm-hmm.
Sumendra?
Yeah, Professor, yeah.
Now, what I'm going to say here is important. You want to predict what this plane took. So one approach could be look at the, these are airliners. So they fly these routes all the time, right? So look at what this plane did last Saturday or the last 10 times or 20 times that it flew that route, right? And so you can predict, given the conditions,
Yeah.
these values. Do you see that?
Yeah.
And so build a model from that, right? And then once you build a model, you give it this input, and then it hopefully predicts, sorry, not this input. You give it this input, and hopefully it's going to predict the sequence that you're going to take. Do you know what I mean?
Yeah, Professor, yeah.
Remember that you're building a model based on training data. So actually, this turned out to be a great example, Sumendra. So let me, you want to predict these values, right? You want to predict these values, these values, these values. But you can train this with hundreds and hundreds and hundreds and hundreds of flights.
Yeah.
Flying, I guess, you have to define that it's got to be Malaysian airline.
Or we can just take one flight, right? If something is like missing and we are keep on training our model like per flight basis. And then if something wrong happens, then we can use their data from our earlier that we used to train our model. And then we can feed them and then try to trace, that
Yes.
could be like more practical, like applicable approaches that we can use the use of RNN. That's what I came up in my head when you are talking about the birds direction and all.
Yeah, that's what I'm saying, that you would feed it, hundreds of flights, right? But in a sequential way, build a model, because remember, this is the model, the hidden layers. Then you feed it the inputs of the actual Malaysia flight, and then it's gonna predict, the direction that it might have taken on that day, given those circumstances.
Yeah.
Obviously, if the pilot intentionally did something, you don't have that because you've never had a pilot intentionally do something like that. But you do have, assuming it was a regular flight and it was an accident, then you would know their position, because at the end of the day, it might seem trivial, but if you're the Navy, and covering that box in the ocean, well, you might be able to cover that in a boat, right? Or that.
Yeah.
And
we can really narrow down our source point.
you can narrow it down. If there's still 3 people alive there floating in the ocean, time is of the essence.
Yeah.
Does that make sense?
Mm-hmm.
Sumendra?
Yes, Professor.
Yeah, so knowing if they ended up here versus here is crucial. You see that?
Yeah.
Okay. Does this answer your question?
Yeah.
Okay, perfect. All right, let's move on then. So I want to I want to talk to Joe, just kind of see if he's willing to model something in finance, but I want to do obviously the classic example, I need to say, of RNNs is natural language processing. You see that? So today, in the second half of the class, so this first hour, I just want to motivate, how you could use these techniques. But really, I'm going to get, so I was saying today, I'm going to talk about this in I'm going to give you an example using MNIST with images, but then the homework is going to be an NLP. It should be very fun homework assignment. So I should say NLP is as a perfect medium for RNNs. I don't know because, it's proprietary, right? But I'm betting Alexa, you guys know what Alexa is, right? Alexa from Amazon, speech system. I'm betting Alexa possibly uses RNNs, at least in some areas, okay? So why does it make sense to use RNNs in NLP? Well, it makes sense because if I say the car is going really what would you say here? Blue? Would you say the car is going really blue?
No.
Slow.
Slow, right?
Yeah.
Or possibly fast, right? So you would say it's either going really slow or really fast. And actually, if you had to choose between the two, which one would you say?
Possible is fast, I think.
Fast, right? Yeah, exactly. And so you just there in your head you said, well, it could be going slow. Why did you say fast? Because probably whenever you've seen this expression, it's in your head. The first thing that comes to mind is that it's fast because your RNN in your brain, you know, has built that model. Does that make sense, guys? And
Yes.
so this is what we're doing, right? So this is another example. The car is going really fast. And so NLP can be used for this quite well, right? So you learn basically how to model things based on sequence. Okay, so your problem, your homework assignment will be something like this. So we'll talk about that, you know, about the homework, but I think it should be pretty good exercise. And you will build literally a model that will predict based on your text, you know, what's the next word to guess. Okay, and the classic example of this is also part of speech tagging. Part of speech tagging is, you know, the part of speech of a sentence, right? So what part of speech is it? So for instance, here I'm going to say this is a determiner, right? And this is what, a noun? And oops, barely looks like a noun. A noun, right? And so on, right? Verbs, etc. So you predict that this is a determiner, this is a car, sorry, a noun, by also creating an RNN. So in this example, you actually want the sequence of part of speech tags given the sequence of inputs. Does that make sense? Yeah?
Yeah.
Okay, great. So your homework assignment, which I will talk about at the end of the lectures today, will be a very, very nice. I found this online, so the code is there, but I really want you guys to, it's really about thinking, you know, of what's going on, okay? And making it like the code that I'm gonna give you. So I'm gonna give you code for MNIST, and then I'm gonna ask you guys to do it for speech. All right, so the last one is, if Joe is there, I don't know if he's still, Joe, are you there?
Yeah, I'm on mute. All right,
Okay.
just unmuted.
Yeah, Joe. All right, so I'm just going to kind of make up a finance scenario, and then maybe you can chime in, right? So let's say that Joe wants to predict in a week, you have Monday, Tuesday, Wednesday, Thursday, Friday, right? And you have the stock market or something. And then you want to predict, I don't know, but let's say trade or not, buy stock. Let's say, you know, I don't know. So this is where I'm going to need your help, Joe, but let's say you want to stock, right? So, you know, you have basically various stocks. Let's say you have from 1 to 500, right? Like an S&P 500 or something. You have the 500 stocks. You're going to pick one to buy. And then you have your inputs would be something, right? So that's what you have to, you build an RNN. And this I'm sure is not at all what you are trying to do, but this is just an example. So if I want to pick the stocks, how they will, maybe you don't want to pick a stock, maybe you just want to know how the stocks are going to do over time, right? And so you want to know, which stock is going to be here and then which stock is going to be here, right? So it's going to give you the stocks given some information, probably also from the stock market, right? And also maybe a little bit from social media, is there a pandemic or not a pandemic? Things like that. Does this make sense, Joe?
Yeah, so if you could figure out this algorithm, you'd be a billionaire. But this is a common scenario.
Yeah, exactly. So this is the, in finance, like I said, you have, I don't know what inputs you have here. I don't know what outputs you have here, but basically this is going to, in its simplest form, it's going to give you stocks to pick each day, for instance, for, an entire year. Let's say you just basically feed all the data from previous years, and then on 2020, you give this model, you're gonna get these inputs from like real time somehow, right? And then you just, you let it rip, right? You just let that algorithm buy the stocks, and then at the end of the year, you're gonna know how you did or not. So like I said, Joe is working on something with finance, so it should be pretty interesting when he gives us he gives the presentation. So I guess the question that I asked to you, Joe, is there anything else that you need me to talk about here, or any questions for your finance project?
No, I'm still thinking about it because I've done some of the stuff you discussed already.
Okay.
With the RNN and LTSM stuff. The only thing I'm using is TensorFlow is Keras, which
You're using
seems
Keras. Okay. Just bear in mind that for the class, we're not going to use Keras, or for the homework. But all right. So anything else? So okay. So it seems like that's basically the idea. So I wanted to cover this scenario, sort of in finance. Okay, so I've given a lot of examples, right? So at this point, I think I've kind of motivated the topic as much as possible. And so are there any questions about this before we move to the actual code? All right, no questions then? Okay, good. So we're going to go back then to the document. Okay, so we're going to go back to our document here. And now I'm going to go over recurrent neural networks, right? So remember that, we're going to do this, like I said, we look at the low level TensorFlow code. Okay, so here we go. So, let's get started then. So recurrent neural networks. So really the code is very similar, okay? So it's gonna be very similar to the code we have looked at in the past, okay? Except, as you might imagine, the thing that changes quite a bit is the inference function. So the inference function is gonna change. The placeholders are gonna change a bit. All right, so the inference function is going to change, the placeholders are going to change, and then when we feed the input, so reading the input into the recurrent neural network, that is also going to change, okay? All right, so in this section, I will cover the topic of RNNs. This is an important and powerful technique in deep learning that deals with sequence data mining and classification, okay? So and this technique can be applied, for instance, to images and text, but I've already provided, examples of other areas and how it can be applied. So we're going to be reusing a lot of the code. So we'll reuse a lot of the code from previous sections, and I'll only, really talk about the main differences here. Okay, which basically relate to the RNN architecture, all right? So, basically RNNs have something called a LSTM neuron, and it's basically the thing that allows you to create the sequence, right? The sequence of hidden layers, etc. Okay. For the example provided here, I will use MNIST, okay? And then for the homework assignment, you guys will have an NLP problem. So you'll have to basically adapt what you're doing in with the images to the NLP problem. And I think that will give you a pretty much, you know, a good grasp of the topic to see the differences. And as always, you can get the code that I'm discussing here from the GitHub. Please, you know, stop me at any time if you have any questions or something is not clear. All right, so basically here, you know, the first part as always, you define the libraries. We will reuse pretty much all the libraries. And the only new steps will be to invoke the RNN module. All right, so the recurrent neural network module, and we're also going to call the RNN cell, both of these from TensorFlow. Right, and from here, we're going to define our architecture. Okay, so you can see the libraries there, you know, import TensorFlow, and then we have from TensorFlow Python ops, you can import RNN and RNN cell. Okay, so those are the two main modules that we can use. Okay. Once the libraries are imported, the next step is, you know, setting the parameters. Remember that this is usually one of the difficult parts, right? So I'm using the familiar MNIST. So I'm using the familiar MNIST because, as you guys know, images are 28 by 28. And so that will give you a really good reference to figure out, you know, how to dimension your own problems. Okay, so for instance, when we do the NLP problem, we're going to have a vocabulary of 123 words. So that means that we're going to have one hot encoded vectors of 123. Okay, but we will see that later. So dimensions here matter, and it's usually one of the difficult parts. So here we have the parameters. You know, the output parameters. So you can see here. This section is just, I want to reduce, you know, warnings and also print all values as numpy arrays. Those are just settings for viewing on the terminal things. Now, here is the basic idea of the algorithm and architecture parameters. All right, so this is the standard non-sequential pipeline, right? So everything that we've done from the beginning of the semester when we didn't use RNNs was like this, right? And I kind of alluded to that at the beginning of the lecture. So this section is very important as it helps to define the overall architecture of the recurrent neural network, or RNN. And our data set is MNIST, okay? So remember here we have images of 28 by 28, right? And then usually what we do is we flatten them into 784. We feed them into some classifier, and it gives us the class right there. RNNs are different, as I specified. So in the past, we have treated each image as a sample of size 28 by 28 that we want to classify as a handwritten digit, right? In the RNN, we still want to classify each image into one of the 10 digits, right? Which is kind of the example I gave you with the car. So here it's a little less obvious why we're doing it. You just think of it as it's a little bit more convenient because of MNIST is well known by you guys. However, in the RNN, we will not treat each image as a vector of 784 features. Okay, so that's what I had said before. Instead, we will use a sequence modeling approach to classify the image. So let's, right, so now let's move on to the next section. So in the previous approaches, we looked at the whole image as an instance of 784 features and classified it that way. With the RNN, we look at each image as a sequence, right? As a sequence of segments of the images. These are also called sometimes patches, or they're called chunks, right? So we break it into these chunks or segments, and we use this sequence from beginning to end to predict the final class of the image. With RNN, the pipeline would look like this. So, you know, we have an initial image. So imagine now we're going to have to use TensorFlow utility functions to be able to reshape these tensors. Because remember, it's going to be 28, but 28 by however many samples we have. So this might be batches of 100, right? And so that's what we're going to feed into the classifier. Okay. And so, but we're going to take the image and we're going to split it into 28 of these, right? So if you notice, it's going to be 1 to 28. So basically, it's like we take this slice, and that's an input in time, then the next one, then the next one, the next one, the next one, the next one, and so on. Okay? And so we basically feed it like that, and at the end of the day, our output is actually a sequence of outputs, but we only want the last output. So it would be the one, that's the one that would give us the handwritten digit. Okay? So that's basically the approach that we're taking here. So that's the sequential pipeline. So it can be seen in the previous image that the 28 by 28 image is converted into 28 vectors of 25 features each, right? So we basically split each image into those vectors. And then the vectors are fed sequentially into the model. And then with this, now with this definition of how to represent the input data, we can proceed to set the, or define the parameters. Now, some of the parameters we've used in the model are similar to the ones we have used in previous chapters. So for the rest of this discussion, I will only really focus on RNN related parameters. So a lot of this is very similar, except inference, which is a little bit different. So remember, we're thinking now of the image as a sequence of 28 vectors of size 28, right? So you have 28 rows of 28 pixels each, and we need to define this using some parameters. So this is where we start getting into the architecture, right? So when you apply this to your own problem in the homework, you know, you're going to have to modify this. So each row will be defined as a chunk. And the size of each chunk is going to be as a chunk size, right? So we define it as chunk size. So we end up with chunk size of 28, and then on n chunks 28. Okay, so that's the number. So notice how we are defining literally the number of inputs in the model, the number of states, if you will, in the model. And then we still have a standard set of 10 classes, right, that we're going to predict. Okay, so we define that as in classes so that we know that, you know, what the outputs will look like. Okay. Now, once we define those input parameters, the main thing in the architecture is we need to define the RNN layer, right? And that's probably the most complicated part here, that we have to define this RNN architecture, the RNN, you know, inference function. So we will define that the RNN size is 128. What that means is that, you know, we have an input for every state, every time t, and then we have a vector here, which is the hidden layer, and then we have an output, right? So we have an output. This one is of size 128. Why 128? Just like before in every other example, we kind of arbitrarily define, not arbitrarily, but by trial and error experience, you define the size of the hidden layer. Okay, so that's what this is. And that's pretty important. Okay. So we can look at the parameters here. You know, these are pretty standard. Learning rate, 0.001, number of epochs, 100,000 in this case. Remember, these parameters are really important, right? So you should play with them. The batch size, this one is really important because as we start reshaping our images, remember, we're going to have 100 samples of 28 by 28, right? That's usually what MNIST gives us. But then we're going to have to reshape this into strange things, right? That will look like this, or 2800 like this. All right, so just be aware that we're going to have to do some reshaping. All right, this example does a lot of reshaping. I think the homework example, because it's not images, is like NLP does a little less reshaping. So that should be a little bit more straightforward to understand. All right, so we've defined the parameters. To predict a class per 28 by 28 image, we now think of the image as a sequence of rows. And so you have this, right? 28 rows of 28 pixels. So you define chunk size, okay? And then you have the number of chunks. So here we have, you know, 28 chunks, all right? And then we'll do our, you know, because these would have been set, you know, 28 by 28 is 784, right? So we have now 28 of 28 size, and then we specify the RNN size, which is the hidden layer. Okay. And then, of course, down here we have the number of classes, which is 10, all right, because we have 10 handwritten digits, okay? So the output vector is one hot encoded as usual, you know, size 10. After defining the parameters, the next step will be to load the data. So we're going to load the data, and this will be discussed in the next section. Let me go over here. All right, so importing the data. All right, so actually it's 1:19 right now. Okay, so let's stop here. Let's take a 10-minute break. Okay, and we will start at 1:30. Okay, what I'm gonna do is I'm gonna do what I did last week so I don't end up with a huge video. I'm going to save this one, and then we're gonna start a new video when I come back. Does that make sense, guys?
Yeah, sure.
Yeah.
Great. All right, so we'll stop here and we'll start again at 1:30. Okay, so let's take a 10-minute break. I'm going to sign off and then I'll come back. I'll sign back in.